pleasure to have Frank Wilczek here to give us the third Baumick lecture. So we all know Frank from his fundamental work in physics, in QCD, asymptotic freedom, axions, anyons, color superconductivity, and many other topics. And he's the author of popular books. Probably many of you have read his books, which reminds me, my wife wants your autograph. And of course, he's won many prizes. He's won the Dirac Medal, the Sakurai Prize, and of course, the Nobel Prize in Physics for asymptotic freedom. So without further ado, let me give you Frank. He's going to tell you about augmenting reality, axions, anyons, and entangled histories.
Thank you. Thank you very much. It's really a great pleasure to be here, see many old friends who, of course, are still young, and many new faces that seem bright and excited. And I'm going to talk about my job, which is to augment reality. I didn't really have a good job description until recently, when I learned about this concept of augmenting reality, and that's what I said to myself, that's what I do. I try to actually help reality to augment itself. So I've expanded the title a little bit because of some recent discoveries. I've also included a few words about time crystals. This is basically a job talk. I wanted to advertise what I've been up to. I thought it's fun, it's kind of an experiment, it's a different kind of colloquium, and suitable to many levels of engagement, and so here we go. I'll start with axions, and it's especially fitting here that we have one of the inventors of axions, Professor Pache. Would you stand up, please? Here in the audience. So, few aspects of experience are as striking as the asymmetry between past and future. We remember the past. Most of us, other than characters in Arrival, only guess about the future. And if you run a movie of everyday life backwards, it doesn't look like everyday life. Here's an example. If you saw this scene evolving before you, you'd be very surprised. And yet, nevertheless, if you looked very close and analyzed the motion of the different atoms in this picture, you'd find that nothing in the laws of physics was violated. Something very funny happened. There was a lot of shaking on the ground spontaneously that organized itself and shot things up into the air, but energy was conserved, all the laws of physics were obeyed, the forces were what they were supposed to be, and the building reassembled, and then the explosives reassembled, all according to the laws of physics, run backwards. So, everyday experience looks very asymmetric between time forwards and time backwards. And yet, in the fundamental laws of physics, for several centuries, starting with Newtonian mechanics and continuing through most of the 20th century, through general relativity and quantum electrodynamics, as physics became more and more sophisticated, it still had this weird property, which not only was gratuitous, but actually raised problems. If the laws of physics are that way, why does experience look so different? And so it begs the question, why? Why do the laws of physics have that peculiar property? Now, as long as that symmetry appeared to be an exact fundamental feature of physical law, it was unclear that asking why would be fruitful. If you've ever dealt with young children, you know that they'll keep asking why over and over again as you explain things. They say, well, why is the sky blue? Well, because that's its color. Why? But why is it that color? Well, because the sun shines and some of the light scatters. Why? Well, there are these atoms, and the atoms are better at scattering blue light. And why? Because blue light has a shorter wavelength. And keep asking why, and eventually you just have to say, that's the way it is. And it was possible that T-symmetry might be rock bottom, that it couldn't be explained in terms of anything simpler. It's a nice principle, okay? It's a symmetry principle, and it might not be possible to explain it in terms of anything simpler. But that explanation, or that retreat, that fallback became impossible when in 1964, James Cronin and Val Fitch discovered a subtle effect in K-meson decays that slightly violates T-symmetry. Actually, the fine point is what they actually did was not a violation of time reversal symmetry as such. Excuse me a second. Entropy on the march here. But a violation of combined charge conjugation and parity symmetry, so-called CP. But since in fundamental physics it's almost impossible to violate CP without violating CPT, without violating T, because CPT is very difficult to violate. CP violation is, according to most of us, essentially equivalent to T violation. So that implies that T symmetry is not rock bottom. It's not even quite true, but it is very nearly so. It seemed to be true until 1964, even though physics became very sophisticated. Why? Now we can ask it with a new level of sophistication. And the good news is we've almost nailed it. The reason is that the basic sacred principles of modern physics, namely relativity plus quantum mechanics plus local symmetry, the principles that allow us to formulate the well-tested now standard model or core theory of all four fundamental interactions, are very powerful. When you try to formulate theories that obey all these principles, they are very, very restricted. The kinds of interactions you can have are very restricted. That's how we got to the standard model. And when you enforce all those principles on the particles we know about, they allow exactly two possible sources of T-symmetry violation. This was a discovery of Kobayashi and Maskawa. One of those potential interactions exists, not only exists, but beautifully explains what Cronin and Fitch observed, and a lot more that was subsequently discovered. The other doesn't happen. Why? Over the past 40 plus years, there have been several attempts to explain why, this new evolved form of the question of why time reversal symmetry looks so good, but only one has stood the test of time. The basic idea, which was proposed in essence by Roberto Peche and Helen Quinn, was to promote the unwanted term, the unwanted interaction, into a dynamical entity. So in the laws as they come, it's just a constant, but you can, the coefficient of this interaction is just a constant, but you can promote that constant to a dynamical entity, a field, and under fairly generic conditions, well, fairly special, but natural conditions, you find that that field wants to evolve to zero. The new field, like all fields in quantum field theory, in the quantum version of field theory, is associated with a new kind of particle. It's quantum that it can produce. I named this particle the Axion in homage to a laundry detergent. People doubt this story, but here's the proof. See, when I was a teenager, which was not long before I did this, I had seen in a supermarket this detergent on sale. I said, gosh, that sounds like a particle. If I ever get a chance to name a particle, I'm going to try to name it Axion. And a few years later, when there was a problem with an axial current, I saw my opportunity. And since this particle cleaned up a problem with the axial current, it was very natural to name it after the detergent. And I could even use that to get past the rather conservative editors of physical review letters, and this name has become the standard. So what the Axion does is keep the past and the future in balance. Okay, this is kind of a fanciful figure, but it's pretty, so I wanted it. So if past and future get out of balance, if time reversal symmetry threatens to be violated, the axions accumulate in the appropriate ball and keep the balance. Big question, do axions exist? So we've made progress over why questions to a very specific question now about whether particles with more or less definite properties that we can talk about and predict whether they exist or not. And we still don't know for sure, but in recent years, the stakes have risen dramatically. Because not only is this kind of aesthetic problem of understanding why that particular interaction doesn't occur get resolved by axions, but this new kind of particle has important cosmological consequences. You can calculate that axions get produced in the Big Bang, and since they interact very, very weakly with ordinary matter, they would survive to this day. It's sort of like the famous microwave background radiation of photons, except that axions interact even more weakly with ordinary matter than microwave photons, and on the other hand, they weigh more, the background would weigh more than the microwave background. So all in all, it has properties that are consistent with the observed properties of the astronomer's dark matter, even though it wasn't introduced for that purpose. Let me very quickly remind you what the dark matter problem is. When you study the rotation of objects we can see in the neighborhood of galaxies and account for all the gravitational influence of conventional kinds of matter, all the kinds we know how to detect based on gas clouds or stars, we find that the ordinary matter would produce a rotation curve, a speed of rotation around the central object, which looks like this, way off. Far away objects instead obey this kind of rotation curve, and that can be accounted for if there's a halo of dark matter which makes up this difference. There's also a smoking gun for dark matter, the so-called bullet cluster. This is two galaxies that have collided. The regular matter, ordinary baryonic matter made out of protons, neutrons, photons, and so forth, collides. And because that kind of matter does have significant interaction and does have with itself and does have the capability of losing energy to radiation, the particles can slow down when they collide. Whereas the dark matter, if it interacts very, very weakly with ordinary matter and with itself, can't lose energy, it just moves right through. And of course, you can't see the dark matter. If we could have seen this dark matter, if it really looked blue like that, this problem would be solved. We'd know about its interactions with light. This is inferred from lensing of objects behind. You can see how the image seems to be distorted around, and you can plot the inferred mass density.
Do you mind if I...
Please do. Okay, thank you. So the bottom line is that if axions exist at all, they must contribute significantly to the dark matter, and plausibly, they dominate it. So as I say, the stakes have risen quite a bit. So a specter is haunting particle physics and cosmology, the specter of axions. And this is artist's impression of what they look like. Several clever strategies for axion detection have emerged in recent months, and there's a ferment in the field which I find very exciting and gratifying. It won't be easy to detect these particles simply because they interact so very feebly with the kind of matter we're made out of and our detectors are made out of, but many determined people are at work. For example, you can see this is an advertisement for the Center for Axion and Precision Physics in South Korea. They're investing heavily in a program to detect axions, and you can see they're really determined. This is a basic idea, or a kind of simplified sketch. I wanted to show my artistic talents, as well as scientific and expository talents. So here we go. Cosmic axions themselves can't be detected directly, but we know how they interact, so we can try to convert them into things that we can detect. And one of the predicted interactions of an axion is with two photons. If we supply one of the photons as a background magnetic field, then an axion can convert into a photon, and the eyeball can see it. That's one strategy. Another strategy, again, once you know, we know how the particle interacts. In a sense, we know exactly what it is, all its properties. We just don't know if it actually exists. And so one predicted property of the axion background is that if you have a large magnetic field and the axion background interacts with it, it produces currents that circulate around the magnetic field direction. Those currents produce, magnetic currents which are in the magnetic field direction. Those currents produce axial magnetic fields that would be oscillating and time dependent, and you can try to detect those. Now, there are very, very sensitive ways using things called squids, superconductor quantum interference devices, to detect weak magnetic fields. So I'm not going to expose the details of this scheme, but it's a very pretty picture and might work, so I thought I'd show it. And there are others. Finally, a very interesting development is that axions, if they have the appropriate wavelength, can form atmospheres around black holes. That's what this is depicting. It turns out that if you have a spinning black hole, axions are so light that their Compton wavelength can be as large or comparable to the size of the black hole. There's a process called superradiance, whereby the black hole would convert its angular momentum into axions. This is a process that's thermodynamically favorable and occurs spontaneously. And black holes would spin down, and these atmospheres would modify their properties. And now, in the era of gravitational waves, we'll be getting information that could lead to the identification of this kind of effect. Okay, so that's a little introduction to axions. Now I'd like to move on to anyons. So, since the discovery of wave-particle duality and its elaboration in quantum theory, we understand that all forms of matter are composed of basic units that are the same thing. They can be called wavicles or laves. Actually, yesterday I discovered the correct name, which is quarticle. There are qubits, so there should be quarticles. Quantum particles are quarticles. Okay. So light is no different from electrons in this respect, even though superficially it seems extremely different. Light has particle-like properties, and electrons have wave-like properties. Yes. However, so that's a wonderful unification of the description of nature. The contrast between gross matter and light has been a theological theme in many cultures, and ours too. Yet they're the same thing, we find out. However, when we consider the behavior not of single quarticles, I have to get used to that, but of groups of them, we find that they divide into two great kingdoms. They're not unified after all. There's a kingdom of bosons and a kingdom of fermions. Bosons are collectivists. They like to do the same thing. Technically, they like to occupy the same quantum state. Photons are bosons, and a laser beam is an excellent example of their bosonness in action. When you have a lot of photons doing the same thing, so they have the same wavelength and the same spatial characteristics, and another potential photon encounters them, there's something called stimulated emission, and that increases the probability that an atom will emit such a photon, and this can be a self-reinforcing process that leads to a laser beam. Fermions, on the other hand, are individualists. They hate to do the same thing. In fact, they totally refuse to do the same thing. This is called Pauli's exclusion principle, and it's responsible for the existence of the periodic table. It's why atoms don't collapse when all the electrons want to accumulate on the nucleus. And it's also responsible for the solidity of matter, because the electrons in different atoms don't want to occupy the same space, among many other things. So, profound. The duality is reintroduced. Maybe we can overcome it with supersymmetry, but that's not the story I want to tell about today. I want to move in a different direction, not towards unity, but towards understanding the origin of that duality more deeply and drawing out implications for other parts of physics. So in a three-dimensional world, or if space has more than 3 dimensions, that's all there is. But in a two-dimensional world, in flatland, things get much more interesting, theoretically. Less is more. The reason is closely related to the theory of knots. I made up a very good pun, I think, a few days ago, which is knots are not knotty in 4 dimensions. And that's the key. See, in 4 dimensions, you can always pull 2 strands of a knot through each other. Because, think about it, the danger is that they would intersect each other as you try to pull it through. But we have an extra dimension. We have a 4th dimension. We can think of that as a temperature on the strands. So the position in the fourth dimension is the value of the temperature. Now, if the two strands have the different temperatures, then we can move them through, and they don't really intersect. It appears like it, but in the extra dimension, they're not intersecting. If the temperatures are the same, well, we heat one up temporarily, pull it through, cool it back down, and again, we can pull through. So there are no knots, no non-trivial knots in 4 dimensions. And similarly, there are no non-trivial knots in 3 + 1 dimensional space-time. And that restricts the possibilities for topology of histories getting entangled with each other. And all that's left is whether particles have been exchanged or not. And that leads to just fermions and bosons, depending on whether you add a minus sign for the exchange or not. So in 2 dimensions, however, you can't pull through. Knot theory in 3-dimensional space or 2-dimensional space-time is a much richer and more complicated subject. So that means, in the context of quantum mechanics, you can introduce rules that vastly generalize the possibilities of bosons and fermions, so much so that I called these things anyons, as in anything goes. It's not quite true that anything goes, but there are lots more possibilities when you have particles in 2 dimensions. Now, that might sound like a totally academic observation because the world is 3-dimensional. However, experimenters regularly do produce 2-dimensional worlds, 2-dimensional universes. They're also known as thin layers of material. Now, you still might say, okay, in the particles that you have in the 2-dimensional materials are still secretly particles that existed in 3 dimensions. So they're fermions or bosons again. But the point is that 2-dimensional particles inside materials can have emergent properties that depend on the background they're in. And just to be a little more technical here, if you have a ground state that's highly entangled and a disturbance in that ground state and move 2 of those disturbances around each other, 2 particle-like and localized disturbances, so they're like particles, and move them around each other, the ground state gets even more entangled and mixed up, and so you can have emergent effects that reflect changes in the wave function that reflect the motion of those particles, those anyons. Now, in some of those materials, including in the so-called fractional quantum Hall effect, electrons fission. They break up into things with smaller amounts of electric charge. If you think about it, it's energetically favorable for electrons to break up into things of smaller charge if they possibly can arrange it. It costs a lot of energy to put a lot of charge in a small place. But usually it's pretty hard to break up electrons or compensate their charges to make fractions. However, in the fractional quantum Hall effect, you can do it. Those are very clever materials. For the electrons, this can be a shattering experience. Here's a picture of the electron about to fission by injection of some extra structure. But their offspring, which are anyons, emerge with brilliant new properties, brilliant new powers. Because, unlike fermions or bosons, whose entire nature can be summarized in terms of symmetry or anti-symmetry of their wave functions, anyons remember their history. Their wave functions remember where they've been. So anyons, I like to say, are particles that have memory. So you see, they're very clever. Some sorts of anyons, if you have several of them, support a very rich collective memory. Okay. Again, if you think about their paths getting entangled and making knots, knots can be very complicated. And if the wave function contains an impression of where those particles have been, then it records what the knot was. This is the basis for a program to achieve quantum computing, which is called topological quantum computing. And if you don't believe me, you should believe that it's serious, because Microsoft is heavily investing in this possibility. Here's a little demonstration of the kind of protocol you would do to make very, very basic quantum computing element. You have a couple of anyons, you wind them around each other, the wave function is affected, and then you measure the effect. I'm not going to insist on the details of this, but that's the basic idea. You imprint a memory by moving the particles around each other, entangling their world lines, and then read it out. Here's what it actually looks like, in false color, of course. When people say that this is what it actually looks like, you can pretty much always count on the fact that it's been heavily processed. But it's some concrete materials that involve superconducting and other subtle properties that entangle their ground state wave functions and support anyons that you can manipulate. Okay, so much for anyons. Now we move on to time crystals. This is a crystal, salt. And it shows breaking of translation symmetry in spatial directions. Okay. The laws of physics are invariant under continuous translations in space. So every position in empty space has equivalent properties to every other position. But in a crystal, of course, it's quite different. The positions where sodium atoms are different from positions where there's nothing, or positions where there's a chlorine atom. And so the symmetry of the crystal is less. You have to translate through a discrete non-zero amount before you get back to the same thing. The idea of time crystals couldn't be simpler. Space is like time. Einstein taught us to try to push that. And so you just ask, is it possible to have materials or systems in which you replace Y by T? Whether you can have things whose behavior in time has less symmetry than the laws of physics. And this turns out to be quite an adventure. Now, we shouldn't think of this as terribly exotic behavior. After all, a beating heart is a sort of time crystal. Okay, it's periodic, so it has time structure, like a crystal. It's not beating all the time, so one moment is different from another. But this is biology, not physics, because it's complicated, it's not very precise, and it requires constant feeding and maintenance. So for a physical time crystal, we'd like to do better on all these regards. We want something that's simple, precise, and autonomous. Well, just in the last few weeks, and this is why I've shoehorned it into the talk, physicists have done it, have produced really remarkable examples of materials that have a periodic structure that persists for a very, very long time, that develops spontaneously, and that doesn't require care and feeding. So, well, I just wanted to brag about that, since I took a lot of grief when I proposed this in the first place. So now, let me finally talk about Entangled Histories. Experimental physicists are achieving new levels of control over production and manipulation of entanglement. Much of this effort is inspired by trying to make a quantum computer. Such a computer would have remarkable abilities, but it's very difficult to produce. People are working very hard at it, though. It may be years, maybe decades before useful quantum computers are actually appearing at Walmart. But there are some intermediate stages where you have control over small numbers of qubits, small elements of quantum systems. That's very precise, and it could be fruitful to consider other ways to exploit those new abilities. So in that spirit, I'd like to revisit some very basic aspects of quantum theory and measurement, and this will lead us to an enriched concept of history in quantum theory that we can access using these new abilities, I think. Okay, so we go way back to the first principles. From the perspective of quantum theory, interference arises from the possibility of getting to the same final state through several distinct paths. Then, if we get to the same possibility through several distinct paths, the probability for the overall process is given by summing the amplitudes for each possibility separately, and then squaring, and that's different from the sum of the squares. For interference to occur, the final state of the whole universe, including any measuring devices and the external world, must be consistent with either of the two contributing processes having occurred. So if you want to measure interference, it's crucial to maintain or create ambiguity, to have what I call strategic ignorance. You don't want to know whether A occurred or B occurred. And you don't want the world to know that there's a distinction. That's the only way you can get interference. And so if we want to have histories that interfere, we have to keep that in mind. So if we want to give an operational notion that different things might have occurred historically, we have to create this kind of strategic ignorance. That's in some tension with the idea that measurement disturbs or collapses the wave function being observed, because it means if you observe something, then at all later times it's disturbed, and you can't measure its history at more than one time. To get around this difficulty, we can correlate. Sorry, so you're what? Looking at your, okay, never mind. To get around this difficulty, we can correlate auxiliary bits with the system sequence of states through specific unitary operations, which I'll outline in a second, that do not disturb its evolution uncontrollably. In other words, we can monitor, but not irreversibly measure the system's behavior. So we sample, we monitor its behavior at several different times, but don't disturb its behavior. We don't do a measurement that's irreversible and disturbs its behavior. Later, we can make measurements on those auxiliary bits in principle with great flexibility. And for instance, we can project on entangled states, and as you'll see, that gives us new kinds of information. So that's a lot of complicated words. Let me illustrate the ideas concretely in the context of the classic two-slit arrangement. So in this situation, we imagine having two monitor bits, the same sort of thing I was talking about, one behind each of the two slits. They implement a unitary operation called C0 in the context of quantum computers that tell you whether the particle passed through that particular slit. So here is the unitary operation. If the monitor bit starts down and the particle passes through at the critical time, then the bit flips. If it doesn't, the bit doesn't flip. That's called a controlled knot. And it's a manifestly unitary evolution if we extend this to a linear operation. And here's the arrangement. We have two such monitor bits. We set them both initially to down, and then they become essentially detectors. They flip if and only if the photon has gone through that particular slit. We have to be careful, though, because if we don't actually measure the monitor bit, we can't be sure what state the monitor bit is in. Now, if we just go ahead and measure one of them, we learn which slit the particle went through. And therefore, there aren't interfering paths for the photon to go through one slit or the other. We just get the appropriate pattern for first slit or second slit. On the other hand, if we measure the total spin, even though the photon might do its thing arriving at the screen much, much later or much, much earlier, if we measure the total spin, things are quite different. Then we get, when spin 1 occurs, the amplitude will be d1 plus d2, all squared, divided by 2. You will get an interference pattern. When it's spin 1, we have the symmetric state of the photon with both slits represented. If spin 0 appears, we have the anti-symmetric state of the monitor bits, and that means we have them appearing, the two possibilities appearing with a relative minus sign. We can also consider more involved measurements, but those are representative. We can also do things in the opposite order, measure where the photon lands, and then see what the spins think about that, and you get non-trivial predictions there too. The idea is you can do the same thing conceptually to monitor aspects of a system's behavior at different times. That is, its history. For instance, if we have a spin 1/2 particle, we can monitor but not measure chosen components of its spin at several times, using them as control bits and C0 gates, as we did for the monitor bits on the two-slit arrangement, and then make collective measurements. And then we get information about correlations between different times. We get partial information about histories, just as we got partial information about where the photon went. Again, an example might be helpful after all this complicated verbiage. So, to represent the history of a system, we take the tensor product of its Hilbert space at several times, so we can formulate its state at several different times, and we write the earlier times to the right. That's conventional. And our observables will be temporal operators, things that operate in this space. So very concretely, let's consider two operators A and B like this that measure things, or I'm sorry, don't measure, but well, ultimately will measure, but that operate at two different times, T1 to the left and T2 to the right. Okay, thank you. These operators commute. Even though they don't commute at either time separately, each time separately would give you a minus sign, but if you take both of them, you get two minus signs, and therefore they commute. And if we look, therefore, if we can, when we make a measurement of their common eigenvalues, we can measure their common values, their values at the same time, and see what that corresponds to. If we do that and say measure that both of these are +1, these guys, since they square to 1, their eigenvalues are plus or minus 1. If we get plus 1 for both of them upon measuring, then the eigenstate, the eigenhistory, is this thing. Now, that formula probably doesn't sing to you, but I only want to say one crucial thing about it, which is that it's an entangled history. It cannot be written as the tensor product of a definite state at time 1 and a definite state at time 2. Okay? You can't replace, you can't get rid of all these plus signs and minus signs and i's. You can't write it as a simple product. And that means we've discovered something about the past of our system that cannot be captured by saying that it had a specific temporal sequence of properties or states. What we've learned about it does not correspond to saying that it evolved through some specific sequence of states. On the contrary, what we've learned about it is that it evolved. The best interpretation of the measurement we've made that captures the information is that it's had parallel evolution through several distinct sequences of properties. Several different histories have to be added up. Putting it more dramatically, distinct histories or worlds diverged, but later came together. So, to me, entangled histories are a precise, tangible, mathematical reflection of the intuition behind the many worlds interpretation of quantum theory. We actually produce the many worlds and see physical effects of them. To make temporal entanglement observable as a practical matter, we have to focus on very small worlds that haven't diverged very much and identify interference among them, as we can do using small numbers of monitor bits as sketched above. Or, to put it a different way, we want to nurture Schrodinger kittens that are short of Schrodinger cats. Kittens are much more friendly, they're smaller, and you can get them to play with each other in a way that ferocious cats don't necessarily. So, speaking of kittens, I've now shown you several of my babies in different stages of development, and I hope you've enjoyed this little sampler of my attempts to help reality augment itself. Thank you.
Yeah, thanks a lot, Frank. A really wonderful talk. Are there any questions?
Yeah.
Comments?
Yeah, so typically it seems that a lot of things that physicists like to do is be very precise with the measurements.
Yes.
But as we're starting to learn quantum mechanics, it seems that there's some beauty in not being precise. Do you think it would be possible to somehow exploit this in the engineering world, like somehow use uncertainty to our advantage?
I didn't plant this question, but yeah, this philosophy of strategic ignorance I mentioned is a very good example. And it's an example. It's one instance of a much broader concept called complementarity that Niels Bohr was a great advocate of. So let me start with complementarity, and then I'll elaborate into strategic ignorance. So complementarity is the concept that there can be different aspects of a system or different perspectives on its properties that are each separately valid points of view and each separately reveal things about the system, but you can't apply them simultaneously. The classic example, which Bohr got inspiration from, was the issue of the position of a particle or the momentum of a particle. The primary reality in quantum theory is a wave function for a particle, but to get something observable, you have to process it. And you can process it in different ways. If you process it in one way, you can get predictions for where it is. If you process it a different way, you can get predictions for how fast it's moving. But these two ways of processing conflict with each other, so you can't do them both at once. Each is perfectly valid, each teaches you something, but you can't do both at once. Strategic ignorance is kind of a special application of that. If you want, and I gave an example, gave a couple of examples of it. It's that if you have two processes and you can determine which of them happened, then you add their probabilities separately. So you square their amplitudes separately and add them. But if you can't tell which occurred, then you get this extra interference term. And if you're interested in the interference term, which teaches you something about the process, the system, that you couldn't access otherwise, you have to be ignorant of which one happened. So it's actually a creative use of ignorance, or trading ignorance about one thing to learn something else. You have to be strategic about that. So I think that's in the spirit of your question. If not, we can have a second round. Okay, thank you.
Are there any other questions? Frank is very friendly, so you can ask.
Yes.
Could you say a little bit more about time crystals and like how they're different from like a pendulum? Like,
Well, a pendulum runs down. A pendulum is not, so it's not, doesn't have this kind of autonomy and self-repairing properties. But if you take away the air and make the pendulum more and more perfect, eventually it gets to be a better and better time crystal. But it's very difficult to make it insulated from the thing gets more and more interesting, the more natural is the separation between your system and the natural and the rest of the world. So if you have systems that are robust against perturbations from the external world and yet maintain this kind of oscillation, that's the exciting kind of time crystal, I would say. Yes?
So about axioms and potential observations in
Yes.
cosmological structure formation.
Yes.
Is there some imprint which is not expected, what cosmologists call cold dark matter?
Well, axions are a form of cold dark matter. Because of the equivalence principle, therefore, if you know its energy distribution, it sort of doesn't matter if it's WIMPs or axions or a wide variety of other things, as long as it's got more or less the same distribution of positions and momenta. There is, however, an effect that axions could significantly differ from other kinds of cold dark matter, which is their evolution in the early universe is different because they're effectively massless fields. That means you can get, and I'll have to be a little more technical here, something called isocurvature fluctuations, as opposed to adiabatic fluctuations in the microwave background radiation. And so observation of isocurvature fluctuations would be very encouraging for axions. So far, they haven't been observed, and so that's not so encouraging, although, but it certainly doesn't rule it out.
Let's thank Frank again.
Well, we have a couple. Let's take two more. I saw two more. Go ahead. Yeah, go ahead. Go ahead.
I have a first question and then comment about the double slit experiment.
Yes.
And you're probably aware that the famous experiment by Tanamura,
By-
Tanamura, a Japanese guy,
Yes.
did an electron at one electron time. So the interference pattern, first of all, it should not call interference.
Slow down. Okay.
It's not interference. It's just that you shoot one electron time.
Yes.
In the slit. Two slits, you get interference now. Right? So it's not interference between the two slits. If you shoot one electron time,
One electron at a time, but the electron is described by a wave which goes through both slits.
Right. So this is...
If you don't measure which slit it's gone through, you're not allowed to say it went through one or the other.
That's one way to understand.
Yeah.
So you mentioned that measure different times. So the point I want to make is interference pattern is not a function of time. So you can shoot one electron at a time. You measure total, let's say 1,000 electrons. You get interference pattern. Or you shoot the electron, 1,000 electrons at the same time, you get the same interference pattern. So in your last example,
Well,
you mentioned that...
no, there are plenty of measurements you can make that aren't sensitive to history, the kind of interference between histories that I'm advocating. In fact, all existing measurements are of that type, basically. But there are observations you can make that do bring out this structure. That's what I'm claiming.
The second point I want to make is that
Yes.
so the interference, to get the phase, basically because the one we detect can only measure the magnitude. The phase information is lost. This is why we get the interference because absolute value is squared.
Yes.
Now, that's the main goal you want to try to how to get that interference.
Yes.
And there's another way to get it. Just if you measure the magnitude, the intensity, or we call it oversampling. If you sample finely enough, actually mathematically that's a way to get the interference, get the phase information directly from the intensity measurement.
Well, that's, yeah, I guess I don't understand the question. That is the usual way to measure interference. You measure the square, and that gives you A star B plus B star A, so it tells you about the relative phase.
So I had a problem. So my point is that if you measure the intensity, and there's a way, from the intensity can directly get the phase.
That's the way, yeah. Yes, absolutely, I agree. Okay, the other question? We had another question over here. I guess not. Oh, yes. You certainly get to ask.
Could you elaborate what reality is being augmented and how?
Well, okay, the question is what reality is being augmented and how? And reality is a process, is a work in progress, I would say. What reality meant to primitive humans was limited by their sensory apparatus, right? They really had no concept that stars are very far away, or that there were little creatures that cause disease, or many, many other things that we know about through the use of instruments. And as we've gotten more and more sophisticated about the instruments we use accelerators, we use giant telescopes, we use radio dishes, and so forth. Our notion of what is real, of what we can share with different humans, reliable information that we can share with other humans, gets bigger and bigger. So when I talk about augmenting reality, I mean, I want to keep expanding our understanding of what reality is. So we've sensed through its gravity the dark matter. We'd like to know really what else it can do. What is it more tangibly? We have classical notions of history. What does history mean in quantum mechanics? Is that something we can add to our vision of reality? Is it a richer concept? We have bosons and fermions. Is that all there is? Can we enrich our concept by appealing to materials and manufactured universes, so to speak? So those are examples of augmenting reality. I'm not sure that's what you're asking about. You're asking about, is there an ideal limit where you capture reality, full stop? And if there is, we're nowhere near it, is all I can say. And physics is not the whole story. There's also trying to understand emergent properties like the emergence of mind from materials. Okay? I think it's quite plausible, and I think most neurobiologists are working under the assumption that the basis of mind is physical materials, suitably orchestrated, just as we know in the case of computers that can do very impressive feats, that they're made out of materials. In fact, we designed them. But the details, or even with a very broad definition of details, the details are unclear. And so we'll augment our understanding of reality, of what reality is, and understand ourselves better when we have a better control or a deeper insight into how that works.
That's scientific exploration. That's the basis of it.
Yes.
Exploring newer.
Yes.
Expanding
Yes.
the horizon.
Yes.
That's what you.
Yes, I mean, by augmenting reality, I guess I wanted to make it sound sexier. It just means, it just means understanding more things better. Yeah. All right.
Can you comment on the promise of topological quantum computing versus doing quantum computing by other methods like superconducting qubits?
Well, I can comment, but you shouldn't trust what I say because or what anybody else says, because I think it's very much up in the air. There are competing programs of experimentalists and approaches. What I will say is the following. Okay, so at present, and this is a little technical, but it's a technical question. Okay, superconducting qubits actually exist in small numbers, and there are actually modest operating quantum computers that you can go on the net and tap into IBM's computers and do little calculations, if you want, quantum computers. Like you can factorize 2. Or maybe even 3. Maybe even 4, I don't know. That's probably too hard. So that is good. I mean, they have the qubits, and they even have modest gates that operate on these qubits. But the prospect of scaling it up and doing error correction and so forth gets quite daunting. Whereas for topological quantum computing, at present, it's debated whether anybody has actually produced a single qubit. I mean, Charlie Marcus thinks he has, and probably has, but certainly hasn't demonstrated logical operations on them. However, it scales much better because the qubits are much more robust against perturbations from the outside world. So once you've mastered the technology for small numbers, it scales much better. So the race is on. I like anyons, but I think that's the long-term future. But in the short term, meaning 10 or 20 years, some other strategy might be better.
All right, thanks a lot for those thoughtful answers. Very good.
Okay.